Apart from position time, velocity time, and acceleration time graphs for the two-dimensional motion, there is one more graph possible to be represented. I'll show it to you now. So this is the image of the tracker file. You can see the x-axis and the y-axis here, and these rhombus shapes, they basically represent the positions of the ball across x and y axis at various instants in time, right? So if you can quickly see, um, I will be able to actually draw a smooth curve here, right? So let me show you a better version of this. So as you can see over here, this is the graph which I got from by plotting the x and y positions of the ball being projected horizontally. So you must be interested by the fact that this looks like a parabola, but please remember, in this case we have positions on both the axes. We have got position across horizontal direction in the x-axis and position across vertical direction in the y-axis. So there is no time involved in x-axis here. So you really can't compare this graph with the position time graph for constant acceleration motion. Though they are looking the same, they are not. They don't mean the same. They've got two different meanings. Now, what kind of interpretation can be done with this graph? Now, to do that, before explain that, I have to tell you that the time interval between two data points present in this picture is that it's 0.033 seconds. That I know that from my tracker file. If you can see here, the time here right now is 0.00 seconds, right? So if I go to the next frame, it's 0.333 seconds. If I go next, you see that. So basically, I know the time interval between two rhombus shapes over here. Basically, I know the time interval between two data points present on this graph. So going back to the Excel sheet. So now that I know the time interval between two data points, now it actually becomes easy for me to find the velocity across x-axis. How do I do that? Basically, how do I do that is, I'll just show it to you. So I know what I can do is I can find positions at two successive instants in time, right? And then how do I find velocity? Velocity basically becomes change in position divided by time taken. So to give you an example, let me go back to my Excel sheet. So if I go here, uh, so I'm going to take the first two data points. I'm going to assume that the first data point to be 0 here. If you can see across x-axis, don't forget that I'm talking of x-axis. So I'm going to take that as 0. So the second one is 0.067, let's say, divided by 0.033, correct? So that's meter by second. So this basically gives me the velocity across x-axis. And please remember, across x-axis, the object is actually traveling at constant velocity, which means the velocity is the same at all instants in time, which means I can take the change in position at any two intervals of time and I'll still get the same data, same answer. But how about y-axis? In the y-axis, the object is actually accelerating, which means if I go by this method, if I go by the method of using uh, change in velocity, change in position by time taken, I will actually get average velocity. I'll not be getting instantaneous velocity. Okay, now that we are talking of instantaneous velocity, if you think that by drawing a tangent to this graph, that I'll be able to get instantaneous velocity, you're mistaken. Why? Because as I told you, across x-axis, we don't have time here. We have position of the ball in the horizontal direction. So by drawing a tangent, we will not be able to get the instantaneous velocity. Rather, we get how the position of the ball across y-axis is changing with respect to the position of the ball across the x-axis. That's what we get if we draw a tangent, which I just got no significance in this context. So hope that is clear. There is one more way of looking at this graph, interpreting it, which you will know after the next video. Thank you.